Hello, in this video we're going to talk about the particulate nature of matter, how particles behave in aqueous solutions. It's important that you understand how these particles behave as we look at aqueous solutions and how they behave. And so, being able to remember what you learned when we did nomenclature, particularly in terms of naming ionic compounds, is going to be important. For you to be able to identify compounds, you have to understand bonding, be able to differentiate between an ionic and covalent compound. Covalent compound, of course, arises from the sharing of electrons, whereas ionic compound contain ions or polyatomic ions. And it's from opposite charges actually attracting one another. And covalent compounds, we can oftentimes have partial positive and negative charges, and they'll come into play as we look at the dissolution process and some other things, which brings in to mind intermolecular forces. And what we learned when we studied those, they're the London dispersion forces from the partial disruptions of those electron cloud around atoms. And individually they're weak, collectively they can be very strong. They're dipole interactions. We're talking about charges and separation of charges in covalent molecules. There's both partial positive and partial negative charges we talked about. There are also ion dipole interactions that we'll look at when we look at how ionic compounds dissolve in water. And then the special case of dipole-dipole was hydrogen bonding. And so we need all of this background material going forward as we talk about the particulate nature of matter in aqueous solutions. So let's look at sucrose, table sugar. We got a couple of sugar cubes here. And here's a structural diagram of sucrose, and where each of these vertices are, they're actually carbons, and for simplicity's sake, we've left those off. This is a molecular compound. There's covalent bonding that holds it together. We can recognize that by all the nonmetals that are in there. And the OH groups, they're not hydroxide groups. They're actually hydroxyl groups, or alcohol groups, functional groups in these molecules. And so let me redraw one of these anyway, from the shorthand notation that's in the structural formula, to show you that the oxygen that's bonded to hydrogen. And really I should have drawn that with a bent angle to it, because it's tetrahedral electron geometry. There's a bent shape around there because of those non-bonding pairs. But that oxygen's got a partial negative charge due to its electronegativity and the non-bonding pairs of electrons on it. And that hydrogen's got a partial positive charge. And so that hydrogen bonding is what helps hold this sugar crystal together in the solid state. And so we have this extended three-dimensional array of these sugar molecules held in place. And so how does it dissolve in water? So water, let me make sure I draw it in its bent conformation. Those hydrogens have a partial positive charge compared to oxygen with a partial negative charge. That little lowercase Greek delta, partial charge. It's not electrons aren't moving from one atom to another to give a complete charge as with an ionic compound. So you just partial charges. And so how water comes in and plucks off all those sugar molecules is by hydrogen bonding, in that the water molecule there's a hydrogen directly covalently bonded to an oxygen. It gets strongly attracted to some other oxygen in the sugar molecule. And likewise, the hydrogen that's in the hydroxyl or alcohol group on the sugar molecule can be strongly attracted to the oxygen that's in the water molecule. And so by hydrogen bonding, that's how this molecule dissolves in water. It does not dissociate. It remains in a molecular form. They're distinct molecules that we see here. Now let's look at an ionic compound. Let's look at sodium chloride. And here we've got a picture of the three-dimensional array of sodium ions surrounded by chloride ions. And the sodium ions are the gray spheres. They're a lot smaller. Remember, they've lost an electron. And the chloride ions are a lot larger. They've gained an electron. And so there's this three-dimensional array, and we want to look at how water interacts to come in and break apart that solid. And so these ionic compounds are going to dissolve, but they're also going to dissociate. And by that we mean that they're ions formed in solution. They're ions in the solid phase, and they're going to be ions in this aqueous phase. And so if we look at this diagram down below, we've got a sodium ion that's surrounded by water molecules. And the way the orientation of the little water molecules are, we've got oxygens, those are the red balls, red spheres. You got a partial negative charge, compare the partial positive on the hydrogens. And they're being strongly attracted to strong attraction between the positive charge and the partial negative charge on the water molecule. So there's the partial negative charge on the oxygen being attracted to the positive charge, complete positive charge on the sodium ion. And likewise, we got these large chlorines, and so you got the chlorine, and now you got the water molecules surrounding it, and the partial positive on the hydrogens versus the partial negative on the oxygen once again, and that's how the molecules become hydrated. We could use that term, the sugar molecules are also hydrated. They're surrounded by the water molecules. Here the ions are surrounded by the water molecules. And so the difference between covalent and ionic compounds is that covalent compounds we don't have ions formed. In the ionic compounds we do have ions formed in solution. So they dissolve, both dissolve, but the ionic compounds also dissociate. So let's see how that comes into play in terms of solutions. We can talk about electrolytes. That are different chemical substances, can either be strong electrolytes, weak electrolytes, or non-electrolytes. And so the first one, the little spheres represent, and they're joined together, these still are as molecules. There are no ions formed. Yes, they've dissolved in water, but they have not dissociated. And so these are non-electrolytes. They do not conduct current. We've got a beaker up above that's got a power supply and a little light bulb and a couple of electrodes in solution, and we're seeing if particles can carry charge back and forth in the solution. There are no electrons that would flow in the solution. Electrons can only flow in the external wire, but the particles in solution, the question is, can they carry charge with them? And if you're a molecular species that's not dissociated, there is not going to be any way to carry charge, and so those are non-electrolytes. Whereas if we skip down the end, strong electrolytes, we've got discrete ions. We've dissolved and we've dissociated. And so now we have these little charge carriers, if you will, these ions in solution that can move back and forth between the electrodes. And that the positive ions will be attracted toward the negative electrode, and the negative ions will be attracted toward the positive electrode. And because they can carry charge, that light bulb burns very brightly. So that's a strong electrolyte. And so molecular species are not electrolytes. Ionic species are strong electrolytes. And there's some that are in between that are weak electrolytes. And these are going to be things that are weak acids or weak bases. And that's why it's important to learn what those strong acids and bases are. And that a weak acid can partially dissociate. And so we can take something like, say, hydrofluoric acid. It's pretty nasty stuff. Weak and strong doesn't talk about how corrosive substance is, just how much it dissociates. But we can look at it in terms of being a Bronsted acid, and that's a proton donor. So the HF can donate a proton to water to make H3O plus and leave behind a fluoride ion. It only does it partially, less than 1%. But if there's a little bit of ions that are formed in solution, and so that light bulb does burn ever so dimly, but it does burn. So that's a weak electrolyte. So non-electrolytes do not dissociate. They don't carry charge. Weak electrolytes partially dissociate, and they're weak carriers of charge, whereas strong electrolytes dissociate totally. They dissociate 100%. So let's look at these 4 beakers and figure out what sort of solutions they are in terms of being electrolytes or non-electrolytes, and whether, if they're electrolytes, whether weak or strong. And so each of the spheres represents an atom. If they're by themselves in solution, they're ions. If they're joined with something, they're molecular species. So if we look at A, we've got some discrete spheres. Those are representing ions. We've got some that join together, they're representing molecules. And so we got both, so this is going to be a weak electrolyte. That's what A is. Whereas in B, all we see are ions. They're only ions. There are no spheres that are joined together. And so this is going to be a strong electrolyte. And that the compound that has made it has dissociated 100%. In C, we see these little molecules, these spheres are joined together. We don't see any solo spheres. These are only molecular species. Only molecules. And so this is going to be a non-electrolyte. And then in D, we see a couple little ions, but mostly this molecules, and so it's going to be a weak electrolyte. And I guess we could compare A and D to see which is the stronger weak electrolyte, which one's dissociated more. And A has more, it's made, like, we can see 3 little white spheres plus 3 red ones, so it's got 6 ions in it, whereas this one, in D, we only got a single green and a single white. 2 ions have been formed, and so A is a stronger weak electrolyte than D. So let's look at one more example and make sure that we're understanding how particles are forming a solution. So let's look at sodium sulfate. And from our nomenclature, we know that sodium is ion just +1, is in column 1A on the periodic table. And sulfate is, we've memorized to be a -2 charge. So sodium sulfate's formula is Na2SO4. And so in this diagram, the sodium ions are going to be represented by a gray sphere, and the sulfate ions are going to be the yellow spheres. Now, don't let the yellow sphere confuse you. It's not just a single atom. That those yellow spheres are really those sulfate polyatomic ions. That if we were to draw the Lewis structure for them, might look something like this. In that sulfur is covalently bonded to 4 oxygens, but we've thrown in 2 extra electrons to give it a negative charge. So that's what that yellow sphere really represents. And so it's an ionic compound. It's going to be a strong electrolyte. That's going to dissociate 100%. So we're not going to have any sort of molecular species left over. So it can't be A because we've got a couple spheres joined together, and we know everything's going to break apart. And this shows some only partial dissociation. Can't be D because we don't have anything dissociated there. We've got 2 sodiums onto each sulfate. We know it's going to totally dissociate. So now the question becomes B, C, or E. Well, how are we going to go about solving that? Well, when we put sodium sulfate into water, it's going to 100% dissociate to make 2 sodium ions and a sulfate ion. So you got this 2-to-1 ratio. And so we need to look at the ratio of the different spheres, which represent the different ions, and find one that's 2 sodiums to 1 sulfate. So in B, I've got 1, 2, 3, 4, 5, 6 sodiums ions, and we've got 1, 2, 3, 4, 5, 6 sulfates. So it's not going to be B. That's a 1-to-1 ratio. If we look at C, we've got 1, 2, 3 sodiums, and I've got 1, 2, 3, 4, 5, 6 sulfates. So instead of being 2-to-1, it's 1-to-2. So it's not going to be C. So that means it's going to have to be E. But let's check to make sure. I've got 1, 2, 3, 4, 5, 6 sodium ions represented by the gray spheres. And then we've got 1, 2, 3 sulfate ions represented by the yellow spheres. So that gives me my correct 2-to-1 ratio. And so the best representation showing the dissociation of sodium sulfate and water is structure E. So that's a little bit about the particulate nature of matter as we dissolve ionic and covalent compounds in water. Thanks for watching.